So in this video, we're going to talk a little bit more about limits, and then we're going to jump back into continuity, which I mentioned in the last video. So let's go over some things that limits can reveal about a function. So what would you know if I told you that the limit of some function f of x, I'm not going to tell you exactly what it is or draw it out, but what if I told you that that function, as x approached 2, was infinity? Well, now you know that no matter which side I approach 2 from, or once again I should say does not exist, now you know that as I approach 2 from either side, that function has to go to either plus or minus infinity. So it would be something like this. Here are my axes. Here's where x equals 2. There's 1, 2, 3. You know that it has to do something like this. Either has to approach like that and that. Let's see, it would go like that and that. Down there, up there. Maybe it does something like that. Maybe it does something like that. Or something like this. But either way, you know that at 2, it's broken. There's something that's making it so that they do not meet together. They're both going to infinity. So that is a discontinuity. It's an infinite discontinuity is actually the technical term. Now, what if we said that the limit as x approached 2 was 5 of f of x was 5, but that f of x, f of 2 does not equal 5. So what does that mean? Well, once again, here's our axes. So we know we have to approach 5 somehow, and let's just pretend we knew that it was a linear function, so it was just a straight line. So we have to approach, once again, at 2, 1, 2, 3, 4, 5, we have to approach that point right there. So something, like that, in there like that. However, it doesn't actually equal 5 there. There's some discontinuity, and better yet, for an even better hint, let's just say f of 2 equals 7, or 3, so we don't have to keep going up. So we know that at 2, f of x equals 3. So that's how you'd represent that. The filled-in hole means equals to at that point. The open hole is a hole. It's a point where the function is not continuous, but up and trivially on either side, it's close to that value. So this is a removable discontinuity, where it's basically a function, but you just have one point that's missing. The other type of discontinuity is called an oscillating discontinuity. That's, if you had a function that went like this and oscillated a whole bunch in there in the middle, that's an oscillating discontinuity, because the more you keep zooming in and zooming in and zooming in, it's still just an oscillating mess, and you can't determine what the value of that function is. But you're rarely going to see anything like that. The point is, you should be able to look at a function and be able to tell what the limits are just by looking at it. So if I draw this, whoops. So if you were to look at the limit right here, we have a jump discontinuity. Here we have, this is called a cusp. Well, I'll talk about that in a second. Here we have an infinite discontinuity, and here we have another jump. And then let's say on this side of the function, it flatlined out. It was a horizontal asymptote at 0. So the limit at negative infinity would be 0, because as you keep marching over this way, you approach 0. As x goes to negative infinity all the way over there, the function approaches 0. It doesn't actually ever get there because it's an asymptote. Should have seen that in your other classes, but the limit is still 0. Right here, you would have to break the limit up into, as it approached, let's call this point -2. The limit of -2 from the left is that positive value, And from the right, it's negative 2 from the right is that negative value. That one right there. That corresponds to that. That corresponds to that. Here we have a cusp, so you can actually say what the limit is because you can plug in the function at that point. You could say, oh, this is, I don't know, 2 or something like that. Now, we'll get into cusps later. Don't really worry about it right now. This is an infinite jump. You can't. It does not exist because they go to infinity on both sides. Here we have another jump, so you'd have to do the same thing we did over there. And here, it looks like it bends back a bit. It should have drawn that a little bit better. But if it were to go, like that, and just start going steeply up, we have another a limit that does not exist because as x goes to infinity, y goes to infinity. So that's just a little bit more about limits. That's probably also all we will do on discontinuities, at least for a while. So this was just kind of a supplemental video. Next time we will probably get into the more rigorous uses of limits in calculus. See you next time.